Welcome back. In this video, we're going to look at examples of finding arc length of polar curves. Let's get to it. All right, so here's our first example. We want to find the arc length of the curve represented by the polar equation on the given interval. And our polar equation is r equals the square root of 10, and we want to find the arc length of the curve represented by this equation between theta equals 0 and theta equals pi. All right, and so if you're familiar with the graphs of polar equations, r equal to some constant is just a circle centered at the origin with a radius of that constant. So in this case, if we were to sketch a quick graph of this polar curve, we would have a circle that looks like this, where the radius of that circle is the square root of 10. All right, and so what we want to do in this case is calculate the arc length of this circle or of this curve from an angle of 0 to an angle of pi. And so this angle right here, that's an angle of 0, and then we have an angle of pi divided by 2, pi, and 3 pi divided by 2. So the arc length that we want to calculate in this case will be this part of the curve right here that lies between an angle of 0 and an angle of pi. All right, so really what we're doing here is calculating half of the circumference of this circle. All right, so let's calculate this arc length. In order to calculate it, we need to know the formula for calculating arc length of a polar curve, and that formula looks like this. The arc length is equal to the integral from alpha to beta of the square root of r squared plus dr d theta squared times d theta. All right, so alpha and beta are the two angles of theta that you want to calculate the arc length between, and then r corresponds to your polar equation, and dr d theta is the derivative of your polar equation with respect to theta. So in this case, r is equal to the square root of 10, so dr d theta will be equal to the derivative of the square root of 10. Now the square root of 10 is just a constant, so the derivative will be 0. And so now we have r and dr d theta, as well as our angles of theta that we want to calculate the arc length between. So now we have everything that we need to set up this definite integral to calculate the arc length in this problem. So if we do that, we'll have that the arc length is equal to the integral from 0 to pi of the square root of r squared, and r is the square root of 10, so we'll have the square root of 10 squared plus dr d theta squared, which is 0, so we'll have 0 squared and then d theta. All right, and so now our definite integral to calculate the arc length is set up. Now all we have to do is simplify it and solve it. And so if we do that, this will be equal to the integral from 0 to pi of the square root of the square root of 10 squared plus 0 squared. The square root of 10 squared is just 10, so we have 10 plus 0, which is 10, so we have the square root of 10 times d theta. All right, so I'll write that in, the square root of 10 times d theta. Now the square root of 10 is just a constant, so the integral of that will be the square root of 10 times the variable of integration, which in this case is theta. So if we integrate, this will be equal to the square root of 10 times theta evaluated from 0 to pi. And so if we evaluate the square root of 10 times theta at pi and subtract the evaluation at 0, we will get this. We'll have the square root of 10 times pi minus the square root of 10 times 0. And the square root of 10 times 0 is 0, so we're just subtracting 0. So we really didn't even need to write that. But what we'll be left with is the square root of 10 times pi minus 0, which gives us a final answer of the square root of 10 times pi. That is the value of the arc length for r equals the square root of 10 between the angles of 0 and pi. Okay, let's take a look at another example. All right, so here's our next example. Once again, we want to find the arc length of the curve represented by the polar equation on the given interval. This time our polar equation is r equals 4 times cosine theta, and we want to find the arc length between theta equals 0 and theta equals pi divided by 2. Now just to get an idea of the arc length that we are calculating here, we know that the graph of 4 times cosine theta is just going to be a circle on the right side of the vertical axis with a diameter of 4, right? If we were to draw a quick sketch of this graph, our circle would look like this. It's on the right side of the vertical axis, and it will have a diameter of 4. All right, so this is where we have an angle of 0, pi divided by 2, pi, and 3 pi divided by 2. And what we want to do is calculate the arc length of this circle from an angle of 0 to an angle of pi divided by 2. So we are calculating this arc length right here. It turns out to be half of the arc length around this circle. So once again, just like with our previous example, the arc length that we're calculating here is essentially half of the circumference of the circle that is represented by our polar equation. Okay, but now that we know what the arc length is that we want to calculate, let's actually find it by using our formula for arc length of a polar curve. We need to determine what r and dr d theta will be. R is just whatever your polar equation is, so we'll have r is equal to 4 times cosine theta, and then to find dr d theta, we just need to take the derivative of r with respect to theta. So if we do that, dr d theta will be equal to the derivative of 4 times cosine theta, and the derivative of cosine is negative sine, so we'll have negative 4 times sine theta. All right, so now that we have r, dr d theta, and we know the two angles of theta that we want to find the arc length between, we can set up our definite integral to calculate the arc length. We'll have that the arc length is equal to the integral from 0 to pi divided by 2 of the square root of r squared, so we'll have 4 times cosine theta squared plus dr d theta squared, so we'll have negative 4 times sine theta squared, and then multiply by d theta. All right, so now we've set up our definite integral. Now we just have to simplify it and solve it to find our arc length. So the first thing that I'll do here to simplify this is square both of these terms. So if we do that, this will be equal to the integral from 0 to pi divided by 2 of the square root of 4 times cosine theta squared. So we'll square each part. 4 squared is 16, and cosine theta squared is cosine squared theta. So we'll have 16 times cosine squared theta. And then we'll add that to negative 4 times sine theta squared. Negative 4 squared is also 16, and sine theta squared is sine squared theta. So we'll have 16 times sine squared theta times d theta. Now the next thing that I see that we can do is pull out a common factor of 16 from both of these terms underneath the square root. So if we do that, this will be equal to the integral from 0 to pi divided by 2 of the square root of 16 times cosine squared theta plus sine squared theta. All right, and now something interesting is going to happen. We know from one of our trigonometric identities that cosine squared theta plus sine squared theta is equal to 1, right? Our Pythagorean identity for sine and cosine says that cosine squared theta plus sine squared theta is equal to 1. So we can replace this quantity with 1. We're just going to have 1 times 16. So inside our integral, we're just going to have the square root of 16, which we know to be 4. So this integral just becomes the integral from 0 to pi divided by 2 of 4 times d theta. This whole quantity just became 1. 1 times 16 is 16, and the square root of 16 is 4. Okay, and so now we have a fairly easy integral to solve here. So let's do that. The integral of 4, which is just a constant, will be that value of 4 times the variable of integration, which in this case is theta. So this will be equal to 4 times theta evaluated from 0 to pi divided by 2. And so now we just have to evaluate 4 theta at pi divided by 2 and subtract the evaluation at 0. So this will be equal to 4 times pi divided by 2 minus 4 times 0. Now 4 times 0 is 0, so that's just going to be 0. We're subtracting 0 from 4 times pi divided by 2, and 4 divided by 2 is 2, so 4 times pi divided by 2 is just going to be 2 pi. So this is equal to 2 pi, which is going to be our final answer. 2 pi is the arc length of this curve, r equals 4 times cosine theta, between the angles of 0 and pi divided by 2. This arc length right here. Okay, let's take a look at another example. All right, so here's our next example. Once again, we want to find the arc length of the curve represented by the polar equation on the given interval. This time our polar equation is r equals 2 minus 2 times cosine theta, and we want to calculate the arc length of the curve represented by this equation between theta equals 0 and theta equals 2 pi. All right, now if we were to draw a quick sketch of the graph for this polar equation, I'll draw the polar coordinate system over here. R equals 2 minus 2 times cosine theta is going to be a cardioid. Whenever you have a constant plus or minus some constant times cosine, and those constants are the same, in this case they're both 2, you're going to have a cardioid, or a graph that is heart-shaped. And when you have a constant plus a constant times cosine theta, your graph will look like this. You'll have a heart shape oriented in this direction. But since we have 2 minus 2 times cosine theta, the cardioid is going to be flipped about the vertical axis. So instead of having the cardioid like this, it's going to look like this instead. All right, not a perfect sketch of this polar equation, but this is the general shape of what it will look like. And we want to calculate the arc length for this curve from an angle of 0 to an angle of 2 pi. So that's going to calculate the arc length of the whole curve. All right, we start at an angle of 0, and then we have an angle of pi divided by 2, and then pi, and 3 pi divided by 2, and then finally 2 pi. All right, so one full loop takes us from an angle of 0 to 2 pi. So the arc length that we are calculating is around the whole entire shape. All right, so to calculate that arc length, we'll use our arc length formula. And in order to set this up, we need to know r and dr d theta. We know that r is equal to 2 minus 2 times cosine theta. So we'll have r is equal to 2 minus 2 times cosine theta, which means that dr d theta, the derivative of r with respect to theta, will be the derivative of 2 minus 2 times cosine theta. Now the derivative of 2 is going to be 0. 2 is just a constant, and the derivative of all constants is 0. And then the derivative of negative 2 times cosine theta will be positive 2 times sine theta, right? The derivative of cosine is negative sine. So negative sine times a negative 2 will give us positive 2 times sine theta. All right, so dr d theta is equal to 2 times sine theta. Now, we can use r, dr d theta, and our angles of theta that we want to calculate the arc length between to set up our definite integral to calculate that arc length. So we will have that the arc length is equal to the integral from 0 to 2 pi of the square root of r squared, so we'll have 2 minus 2 times cosine theta squared plus dr d theta squared, so we'll have 2 times sine theta squared, and then d theta. Okay, so now let's simplify. Let's square each of these quantities. When we square this first quantity, because we have 2 minus 2 times cosine theta, we have two terms. I'm going to use a little trick to square it quickly. We'll square the first term, then add that to these two terms multiplied together, but then multiplied by 2, and then we'll add that to the last term squared. So the arc length will be equal to the integral from 0 to 2 pi of the square root of 2 squared, which is 4, right? That's the first term squared. Then we're going to add that to these two terms multiplied together, multiplied by 2. So 2 times the negative 2 times cosine theta is negative 4 times cosine theta, but then we need to multiply it by 2 again to get negative 8 times cosine theta. Okay, and then we'll add that to the last term squared, and negative 2 times cosine theta squared will be positive 4 times cosine squared theta, right? Negative 2 squared is positive 4, and cosine theta squared is cosine squared theta. So we'll have plus 4 times cosine squared theta, and those are all the terms that result from squaring this quantity. All right, and we don't really need these parentheses here because we're just adding the next term. We don't have to worry too much about our order of operations here. We're just going to be adding all these terms together anyway. All right, but we're going to add this to 2 times sine theta squared, which will be 4 times sine squared theta. Okay, and don't forget d theta. Now the next thing that I notice here is that with these last two terms underneath this square root, we have 4 times cosine squared theta and 4 times sine squared theta. If we pull 4 out of both of those terms, we will have cosine squared theta plus sine squared theta. And from our Pythagorean identity for sine and cosine, we know that cosine squared theta plus sine squared theta is equal to 1. So if we pull that 4 out, that will help us simplify this integral further. And so we'll have that this is equal to the integral from 0 to 2 pi of the square root of 4 minus 8 times cosine theta plus 4 pulled out of cosine squared theta plus sine squared theta. All right, and then we have d theta. Now that we pulled 4 out of those two terms, cosine squared theta plus sine squared theta is just equal to 1. So we have 1 times 4, and so this last term will just be 4. All right, so this quantity just becomes 1. And so if we rewrite our integral again, the arc length will be equal to the integral from 0 to 2 pi of the square root of 4 minus 8 times cosine theta plus 4. all right, and then we'll have d theta on the end. And now what we can do is combine this 4 and this 4, right? We have two constants that we can add together. So we'll have 8 minus 8 times cosine theta. So let's write that. This is equal to the integral from 0 to 2 pi of the square root of 8 minus 8 times cosine theta. And then we have d theta. And now we have a common factor of 8 that we can pull out from each of these terms. We have an 8 in this term and an 8 in this term. So if we pull that out, this will be equal to the integral from 0 to 2 pi of the square root of 8 times 1 minus cosine theta d theta. Okay, so now we can take the square root of each of these parts. We'll take the square root of 8 and pull that out to the front of the integral, and then be left with the square root of 1 minus cosine theta inside the integral. And so if we do that, the arc length will be equal to the square root of 8 times the integral from 0 to 2 pi of the square root of 1 minus cosine theta d theta. Now at this point, it seems like we're kind of stuck, right? We could simplify the square root of 8 a little bit on the outside here, but if we actually want to integrate what we have here inside the integral, it's not initially clear how we can do that. We have the square root of 1 minus cosine theta, but there's no easy way to integrate that in its current form. We can't use u substitution, because if we set u equal to 1 minus cosine theta, the derivative of that is not also within this integral, so that's not going to work. And we also don't know any specific integration rules for the square root of 1 minus cosine theta. So we're kind of stuck here, but what we can do is try to make use of any trigonometric identities that we know that might allow us to rewrite 1 minus cosine theta. And so what trig identity do we know that involves some expression similar to 1 minus cosine theta? Well, one trig identity that is close to that is this identity. We know that sine squared theta is equal to 1/2 times 1 minus cosine of 2 theta. Now that doesn't look exactly like what we have right here, right? We just have 1 minus cosine theta, but it's very similar to this expression right here, 1 minus cosine of 2 theta. What we can do is actually manipulate this identity a little bit so that this side of the equation does look like what we have within our integral. And so the first thing I'm going to do is multiply both sides of this equation by 2 to remove this 1/2, right? 1/2 times 2 is just 1. So we'll have 2 times sine squared theta is equal to 1 minus cosine of 2 theta. And now what we can do to make 1 minus cosine of 2 theta become 1 minus cosine theta is just divide both of these angles on both sides of the equation by 2. Since our angle is just theta, we can change that in this identity as long as we change both of the angles for sine squared theta and cosine of 2 theta. So what we'll do is divide those angles by 2, and we'll have 2 times sine squared of theta divided by 2, and that will be equal to 1 minus cosine theta. All right, theta divided by 2 is theta divided by 2, and 2 theta divided by 2 will just be theta. So now we can see that 1 minus cosine theta is equal to 2 times sine squared of theta divided by 2, so we can rewrite 1 minus cosine theta with that expression. And the reason why that's helpful is because now we'll have the square root of a function being squared. We can take the square root of that and eliminate that square root from the integral. All right, so here's what we'll have. This is equal to the square root of 8 times the integral from 0 to 2 pi of the square root of 2 times sine squared of theta divided by 2 d theta. Okay, and now we can take the square root of both of these parts to simplify further. And so if we do that, this will be equal to the square root of 8 times the integral from 0 to 2 pi of the square root of 2 times sine of theta divided by 2 times d theta. All right, so we took the square root of both of these parts. The square root of 2 is the square root of 2, and the square root of sine squared of theta divided by 2 is just sine of theta divided by 2. All right, now one thing I want to mention before we move on to our next step is that when you take the square root of a function like sine squared of theta divided by 2 in these problems, you need to make sure that the square root of that function, which in this case is sine of theta divided by 2, you need to make sure that that function is positive for the angles of theta that you were integrating between. Because if it's not positive, in this case between 0 and 2 pi, then your arc length calculation will be incorrect. Typically what will happen is you'll end up with an arc length of 0, which clearly is not the arc length of your curve. And so what you have to do to make sure that that doesn't happen, so you don't waste your time and calculate an arc length of 0, is to quickly check to make sure that sine of theta divided by 2 is positive between those two angles of theta that we are integrating over. All right, so in this case, if we were to look at the graph of sine of theta divided by 2, or for graphing purposes, we're going to look at sine of x divided by 2. All right, that's what I'm going to graph here real quickly. This is our x-axis, and this is our y-axis. X equals pi is right here, and x equals 2 pi is right there. And then right here is a y value of 1. The graph of sine of x divided by 2 will look something like this. Not a perfect graph, but as you can see, it is above the x-axis, where it results in positive values between the values of 0 and 2 pi. So we're good here. Sine of x divided by 2, or for our integral, sine of theta divided by 2, is positive between these two angles of theta. If it wasn't positive for all of the angles between 0 and 2 pi, we would have to make some sort of adjustment, whether that be by putting absolute value bars around that function, or adjusting our bounds of integration and using symmetry to calculate our arc length instead. And you'll see that in our last example, but for now, we don't have to worry about that because sine of theta divided by 2 is positive between 0 and 2 pi. Okay, so that's just something to keep in mind. That's going to pop up in these arc length problems. And so I wanted to make you aware of that because sometimes you might end up with an incorrect answer for your arc length if you don't pay attention to that. Okay, but now to simplify this further, we can pull the square root of 2 out to the front and multiply that by the square root of 8. And so this will be equal to the square root of 8 times 2. But 8 times 2 is 16. So we have the square root of 16, which we know to be 4. So I'm just going to erase that. And we'll have 4 times the integral from 0 to 2 pi of sine of theta divided by 2 d theta. All right, and so now at this point, you can see that we have a fairly simple integral that we can integrate. That was the whole purpose of using that trig identity to rewrite our integral so that we could eliminate this square root and have a much simpler integral to deal with. All we have to do to integrate sine of theta divided by 2 is use u substitution. We'll set u equal to that inside function of theta divided by 2, and then we'll be able to integrate in terms of u. So let's do that. Let's go ahead and use u substitution here. I'm going to set u equal to theta divided by 2, which means that du d theta, the derivative of u with respect to theta, will be equal to 1/2. And so du will be equal to 1/2 d theta if we multiply both sides by d theta. And whatever du is equal to needs to be found within our integral, but I don't see 1/2 d theta, I just see d theta. So let's multiply both sides by 2. That will cancel out with this 1/2 and give us 2 du is equal to d theta. So now we can replace d theta in our integral with 2 du. All right, so if we rewrite our integral in terms of u, this will be equal to 4 times the integral from theta equals 0 to theta equals 2 pi. We're going to rewrite those to be in terms of u in just a second, but I wanted to make sure that we remember that those are bounds of theta that we need to change. And then inside the integral, we have sine u times 2 du. All right, now let's rewrite these bounds of integration from being in terms of theta to being in terms of u so that we can just integrate and evaluate with respect to u, and then we won't have to go back into terms of theta. So if we plug these values of theta into what we set u equal to, u is equal to theta divided by 2. So when theta equals 0, we'll have 0 divided by 2, which is 0. So our new lower bound is u equals 0 instead of theta equals 0. So we'll write u equals 0. And then for the upper bound, theta equals 2 pi. We'll plug 2 pi in for theta and have 2 pi divided by 2, which will just be pi. So we'll have u equals pi for the upper bound. So I'll rewrite theta equals 2 pi to be u equals pi. Okay, so now if we integrate, first I'm going to pull this 2 to the front. We'll have 2 times 4, which is 8. So this is equal to 8 times the integral of sine u, and the integral of sine is negative cosine. So we'll have negative cosine u evaluated from 0 to pi. And then we don't need this u substitution work anymore, so we can work on our evaluation up here. And I'm going to pull this negative out to the front, so we'll have negative 8. That will just make evaluating cosine of u at pi and subtracting the evaluation at 0 a little bit easier. So this will be equal to negative 8 times cosine evaluated at pi, which is negative 1. So we have negative 1 minus cosine evaluated at 0, which is positive 1. So we have negative 1 minus 1, and so this is equal to negative 8 times negative 2, which is equal to positive 16. And so 16 is the arc length around this entire cardioid represented by r equals 2 minus 2 times cosine theta. Okay, let's take a look at one more example for this video. All right, so here's our final example. Once again, we want to find the arc length of the curve represented by the polar equation on the given interval. In this case, we have r equals 1 plus sine theta as our polar equation, and we want to find the arc length between theta equals 0 and theta equals 2 pi. All right, so very similar to our previous example, r equals 1 plus sine theta represents a cardioid, right? When you have a constant plus some constant times sine theta, and both of those constants are the same, in this case we have 1 plus 1 times sine theta, then you have a cardioid. In this case, since we're working with sine, the cardioid will be oriented a little bit differently than it was with cosine in the previous example. So if I draw a quick sketch, the cardioid will look something like this. It's oriented in this direction. If we had 1 minus sine theta, then this would be flipped about the horizontal axis or the polar axis. So it would be shaped like this instead, but that's not what we have in this case. We have 1 plus sine theta, so this is what our cardioid is going to look like. All right, but anyway, we want to calculate the arc length of this cardioid between the angles of 0 and 2 pi, so that's going to be the entire arc length of the whole cardioid. All right, we're starting at an angle of 0, then we go to pi divided by 2, to pi, to 3 pi divided by 2, and then back to 0, or an angle of 2 pi. All right, so we're calculating the arc length around the entire cardioid. So now let's set up our definite integral to calculate that arc length. We need r and dr d theta. We know that r is equal to 1 plus sine theta, right? That's what we were given. And so the derivative of that, dr d theta, will be equal to the derivative of 1, which is 0, plus the derivative of sine theta, which is cosine theta. So cosine theta is dr d theta. All right, so now let's set up this definite integral. The arc length will be equal to the integral from 0 to 2 pi of the square root of r squared, which is 1 plus sine theta, so we have 1 plus sine theta squared, plus dr d theta squared, which is cosine, so we'll have cosine theta squared, and then d theta. Okay, and so now let's simplify. Let's square each of these quantities, and we'll start with this quantity of 1 plus sine theta. When we square this, I'm going to use a little trick. We'll square the first term, then add that to these two terms multiplied together, multiplied by 2, and then we'll add that to the last term squared. So if we do that, this will be equal to the integral from 0 to 2 pi of the square root of 1, that's 1 squared, plus 1 times sine theta, which is just sine theta times 2. So we'll have 2 times sine theta, and then we'll add that to the last term squared, so we'll have sine squared theta. All right, and then we'll add that to cosine theta squared, which is going to be cosine squared theta, and then we have d theta. All right, and so these last two terms that we have here, sine squared theta and cosine squared theta, we know from our Pythagorean identity for sine and cosine that sine squared theta plus cosine squared theta is just equal to 1. So these two terms are just going to become 1. So this is equal to the integral from 0 to 2 pi of the square root of 1 plus 2 times sine theta plus 1 d theta. All right, so these two terms just became 1. All right, but now we can add this one and this one together to have 2 plus 2 times sine theta. So let's do that. We'll have that the arc length is equal to the integral from 0 to 2 pi of the square root of 2 plus 2 times sine theta d theta. And then what we can do is pull that common factor of 2 out of both of these terms, right? We can divide this term by 2 and this term by 2. If we do that, we'll have the integral from 0 to 2 pi of the square root of 2 times 1 plus sine theta d theta, and then we can take the square root of each of these parts, and so this is equal to the integral from 0 to 2 pi of the square root of 2 times the square root of 1 plus sine theta d theta. All right, so we just took the square root of each of these parts, so we have the square root of 2 right here, and the square root of 1 plus sine theta right here. Now what we can do is pull the square root of 2 to the front of the integral, and so if we do that, this will be equal to the square root of 2 times the integral from 0 to 2 pi of the square root of 1 plus sine theta d theta. And now this is where things get a little bit tricky. Similar to our last example, we get to a point where we have the square root of some trigonometric expression that we're not really sure how to integrate. We have no easy way to integrate the square root of 1 plus sine theta. And so the first thing that you should try to do is determine if you can rewrite this expression using a trig identity. However, in this case, there's no trig identity that's going to help us. We don't really have any identities that involve 1 plus sine theta. We have an identity that involves 1 plus cosine, but we don't have any for 1 plus sine, so we're kind of stuck here. And so we have to be a little bit more creative and think of another way that we could rewrite this integral into a form that we can hopefully integrate. And so at this point, what I would recommend that you do is multiply by some form of 1 that will allow us to rewrite this integral in some convenient way. And so here's what I'm going to propose. Let's try multiplying this integral by a form of 1 of the square root of 1 minus sine theta divided by itself. All right? And then don't forget d theta. But by doing this, what's going to happen is we're going to have 1 plus sine theta times 1 minus sine theta underneath a square root, and 1 plus sine theta times 1 minus sine theta will be the factorization of a difference of squares. And so let me show you what I mean. Let's multiply this square root by this form of 1. If we do that, this will be equal to the square root of 2 times the integral from 0 to 2 pi of the square root of 1 plus sine theta times 1 minus sine theta. And then in the denominator, we have the square root of 1 minus sine theta, and then we have d theta at the end. All right, now the reason why this is helpful is that these two quantities right here, 1 plus sine theta and 1 minus sine theta, as I mentioned earlier, are the factors of a difference of squares, right? A difference of squares would be a squared minus b squared, and you can always factor a difference of squares by having a plus b times a minus b. So in this case, a is 1 and b is sine, right? We have 1 plus sine theta and 1 minus sine theta. A plus b, a minus b. So we can rewrite these two factors multiplied by each other to be a difference of squares. We can have a squared, which will be 1 squared, minus b squared, which will be sine of theta squared. All right, and 1 squared is just 1, so what we'll have is that this is equal to the square root of 2 times the integral from 0 to 2 pi of the square root of 1 minus sine squared theta divided by the square root of 1 minus sine theta times d theta. Now the reason why that's helpful is because now we can rewrite 1 minus sine squared theta using our Pythagorean identity for sine and cosine, right? We know that 1 is equal to sine squared theta plus cosine squared theta. And if we solve for cosine squared theta by subtracting sine squared theta from both sides of the equation, we'll have 1 minus sine squared theta is equal to cosine squared theta. And so 1 minus sine squared theta, this right here, can be rewritten using cosine squared theta. And then we will be able to take the square root of cosine squared theta. All right, so let's do that. The arc length will be equal to the square root of 2 times the integral from 0 to 2 pi of the square root of cosine squared theta divided by the square root of 1 minus sine theta d theta. All right, and now at this point, we can take the square root of cosine squared theta, but we do need to be careful. This is similar to what happened in our previous example. When you take the square root of cosine squared theta, you need to make sure that the square root of that, which would be cosine theta, is positive between the two angles of theta that we are integrating over. All right, now the graph of cosine, in this case, we're going to look at cosine x, where this is the x-axis and this is the y-axis. Just know that x corresponds to theta in this case. If this is y equals 1, and then we have x equals pi divided by 2, x equals pi, 3 pi divided by 2, and 2 pi, cosine looks like this, and it would continue from there. But as you can see, between 0 and 2 pi, cosine is not completely positive. It's only positive between 0 and pi divided by 2, and 3 pi divided by 2, and 2 pi. So when we simplify this integral, it's not going to be correct for us to just say that this is equal to the square root of 2 times the integral from 0 to 2 pi of cosine theta divided by the square root of 1 minus sine theta d theta. All right, we can't just take the square root of cosine squared theta and leave it as cosine theta, because this is not positive for all the angles between 0 and 2 pi. If we proceed with this integral as it stands, which you could if you wanted to, you'd be wasting your time because in the end, you're going to end up with an arc length of 0. But that's not the correct answer. As you can clearly see from our graph here, this curve that we want to calculate the arc length of is going to have some arc length bigger than 0. So what we can do to fix that is make use of symmetry for the arc length of this curve, right? Notice that this cardioid is symmetric about the vertical axis. So what we can do is calculate the arc length of half of the cardioid and then multiply that by 2 to get the arc length of the whole cardioid, all right? And so we're going to either integrate from this angle to this angle or from this angle to this angle. All right, and so you could do this either way that you wanted. You could go from negative pi divided by 2 to positive pi divided by 2, or from pi divided by 2 to 3 pi divided by 2. Just make sure that you choose the appropriate cosine function to match those angles. And what I mean by that is that from pi divided by 2 to 3 pi divided by 2, cosine is negative, but if we were to continue in this direction right here, at negative pi divided by 2, between these two angles, negative pi divided by 2 and positive pi divided by 2, cosine is positive. So if we change our bounds of integration to be from negative pi divided by 2 to positive pi divided by 2, we could use positive cosine theta. But if we change our bounds of integration to be from pi divided by 2 to 3 pi divided by 2, where cosine is negative, then we need to write negative cosine theta. All right, now that's what I'm going to choose to do. And so here's what that's going to look like. Instead of going from this step to this step, which won't give us the correct arc length, instead of saying that the square root of cosine squared theta is positive cosine theta when integrating between 0 and 2 pi, instead what I'm going to do is change these bounds of integration to be from pi divided by 2 to 3 pi divided by 2, make cosine theta negative, right? Add a negative sign to that because between these two angles is where cosine is negative, and then multiply this integral by 2. By multiplying it by 2, we will be calculating the arc length of the whole cardioid. Without that, we'd only be calculating half of it, from pi divided by 2 to 3 pi divided by 2. All right, so hopefully that makes sense. What we're doing here is trying to avoid wasting time where we would have solved our integral as it was before and found an arc length of 0, which wouldn't have been correct. And we're making the adjustment now so that we do calculate the arc length correctly the first time. All right, so we're making use of symmetry. We're integrating from pi divided by 2 to 3 pi divided by 2. We're multiplying the integral by 2. And since cosine is negative between those two angles, we have negative cosine theta as the result of the square root of cosine squared theta instead of positive cosine theta. All right, and so now we can work on solving this integral. This might initially look pretty complicated, but we can use u substitution here. We can set u equal to 1 minus sine theta. And the derivative of that will also be found within our integral. It will be right here in the numerator. So let's do that. We'll set u equal to 1 minus sine theta. So du d theta, the derivative of u with respect to theta, will be the derivative of 1, which is 0, and then the derivative of negative sine theta. The derivative of sine is cosine, so we will have negative cosine theta. And then multiplying both sides by d theta will give us that du is equal to negative cosine theta d theta. All right, and so du is equal to an expression that we can find within our integral. Negative cosine theta d theta is right here. So u substitution is going to work pretty nicely. This will be equal to 2 square roots of 2 times the integral from theta equals pi divided by 2 to theta equals 3 pi divided by 2 of 1 divided by the square root of u times du. All right, so we replaced 1 minus sine theta with u, and we replaced negative cosine theta d theta with du. Now for our next step, I'm going to rewrite 1 divided by the square root of u to be 1 divided by u to the 1/2 power, right? The square root of u and u to the 1/2 power would be the same. And then in order to integrate that, I'm going to move u to the 1/2 power to the numerator and make that exponent negative. So that will look like this. This is equal to 2 times the square root of 2 times the integral. And I'm going to rewrite those bounds of integration to be in terms of u in just a second, but we're going to have u to the negative 1/2 power du. All right, this is the same as 1 divided by the square root of u. That's just going to make it easier for us to see how to integrate using our power rule of integration. Now for the bounds of integration, let's make them to be in terms of u. We'll plug these values of theta into our equation for what we set u equal to. When theta equals pi divided by 2, we'll have 1 minus sine of pi divided by 2. Sine of pi divided by 2 is 1, so we'll have 1 minus 1. That gives us 0. So our lower bound will be u equals 0, so we'll have u equals 0. And then for the upper bound, when theta equals 3 pi divided by 2, we'll have 1 minus sine of 3 pi divided by 2. Sine of 3 pi divided by 2 is negative 1, so we'll have 1 minus negative 1, which becomes 1 plus 1. So u equals 2 will be our new upper bound. So we'll have u equals 2. All right, and so now we can integrate this and evaluate at our bounds of integration. We can work in terms of u and not have to go back in terms of theta. So if we use the power rule of integration, we'll add 1 to the exponent and divide by that new exponent. So this is equal to 2 times the square root of 2 times u to the power of 1/2 divided by 1/2, evaluated from 0 to 2. Right, we add 1 to this power. Negative 1/2 plus 1 is positive 1/2, and then we divide by that new exponent of 1/2. Now dividing by 1/2 is the same as multiplying by 2, and I'm just going to do that on the outside here. So this will be equal to 2 times 2 square roots of 2, which will be 4 square roots of 2, times u to the 1/2 power, evaluated from 0 to 2. And u to the 1/2 power is just the same as the square root of u. So I'm going to rewrite that like this. We'll have the square root of u. And so this is equal to 4 times the square root of 2 times the square root of u, evaluated at 2, minus the evaluation at 0. So we'll have the square root of 2 minus the square root of 0, which is just going to be the square root of 2 because the square root of 0 is 0. So I'm just going to erase that. And so 4 times the square root of 2 times the square root of 2 will be 4 times 2, right? The square root of 2 times the square root of 2 is just 2, and 4 times 2 is 8, so this is equal to 8. The arc length of this entire cardioid is equal to 8. All right, that is the arc length of r equals 1 plus sine theta from 0 to 2 pi. All right, so hopefully that process made sense. This last example was a little bit more complicated than some of the other ones, but this is probably the most difficult that these problems will get in a Calculus 2 course. You most likely won't see anything more difficult than this, and so if you understood the process of this example, then you're going to be pretty good with calculating arc length of polar curves. All right, and so with that, that was it for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.